Greetings and salutations. This is Monika Wahi, your Library College lecturer, bringing to you Chapter 4.1 Scatter Diagrams and Linear Correlation. So here's what you're going to learn. At the end of this lecture, you should be able to explain what a scattergram is and how to make one, state what strength and direction mean with respect to correlations, and compute correlation coefficient R using the computational formula. And finally, you should be able to describe why correlation is not necessarily causation. So let's jump right into it. First, we're going to talk about making a scatter diagram. And the thing on the right side of the screen is not a scatter diagram, but it's kind of scattered. So I put it there. It's kind of pretty. And then next, we're going to talk about correlation coefficient R and how to make it. And then finally, we're going to do a shout out to causation and lurking variables, which remember we talked about before, but we're going to talk about them again in relationship to R. So let's start with the scattergram, and I also call it a scatter plot because just like everything in statistics, there's got to be about 8 names for everything. So scattergram and scatter plot mean the same thing. So let's just get with the setup here. So scattergrams or scatter plots are graphs of XY pairs. So what's an XY pair? XY pairs are measurements, two measurements made of the same individual or the same unit. So if you measure my height and my weight, that's an XY pair. If you measure my height and then my friend's weight, that's not an XY pair because that's two different people, right? So these XY pairs, the X part is called the explanatory or independent variable, and it's always graphed on the x-axis. So remember in algebra you would do these graphs where you had this vertical line and that was the y-axis, and yet this horizontal line which was the x-axis, and I always had trouble remembering which was which, but that's how it is. And so whichever of the pairs is x, expect that to be graphed along the x-axis, and it's also called the explanatory or independent. Remember, there's got to be a million names for everything. Explanatory or independent variable. So if I talked to you and said, here's an XY pair, and this one is the independent variable, or this one is the explanatory variable, you need to just secretly know I'm talking about the X of the two. And then surprise, here's the Y of the two. And the Y is also called response variable. It's also called the dependent variable, and that is graphed on the y-axis. So again, like I said, I used to have trouble remembering, is the vertical one the y-axis or the horizontal one? But what I did was I remembered, if you take a capital Y and you go grab onto its tail and you go pull it straight down, you'll see that it's vertical. And that's how I remember that's the y-axis. It doesn't hurt the y, it's used to that. So if you can stretch the y's tail down and you get vertical, remember that's the y-axis, and then the other one is the x-axis, okay? And then also you have to find a way to remember which one means what. Like, does X mean explanatory and independent, or what? Or does it mean response independent? So how I do it is, you know how we sing the ABCs, A, B, C, D, E, F, G. Well, if you fast forward, the N is W, X, Y, Z, right? So the X comes before the Y, in the alphabet. So I do X and then an arrow to Y. And then I imagine in my head that saying X causes Y, even though it doesn't necessarily cause Y, as you'll see at the end of this lecture. But I think about it that way, because if that happens, then Y is dependent on X, and X is independent. It can do whatever it wants, but Y is dependent. So that's my way of remembering X is the independent variable and Y is the dependent variable. So anyway, that's a long way of saying the scattergram is a graph of these XY pairs, and that's what we're going to do, is make that graph. So we needed some XY pairs, right? So I asked the question, do the number of diagnoses a patient has, does that correlate with the number of medications she or he takes? So if you don't have that many diagnoses, you probably aren't on that many meds, right? But if you have a lot of diagnoses, you should be on a lot of meds. But we all know people in real life can sort of violate that, just depending. I mean, you could have one really bad diagnosis with a lot of meds, or you can have a bunch of diagnoses that are all taken care of with one med. So it's not perfect, but this is kind of a reasonable thing to think. So what I did was I put up here just 4 XY pairs. as you can see. So I'm got 4 pretend patients. And you can see here's the first patient. That person has an X of 1 because they only have one diagnosis. But like I was saying, it must be a bad diagnosis because that person has a Y of 3 or is on 3 meds for it, right? So that's how you read this table. So let's start making our scattergram out of these data. Okay, so here we go. So I labeled the x-axis number of diagnoses, right, just to keep things straight, and the y-axis number of medications. And then you'll see where I put the dot, right? Because x is 1, I went over to one number of diagnosis, right? No, one diagnosis. And then because y was 3, I went up 3 to this 3, right? And there goes the dot. That's where that first person gets a dot. Okay, you put it there. And that's what you're going to do with these other ones too, is put dots. Okay, I just threw all the dots down so you can kind of see what was going on. But here's the second person, right? So that person had an X of 3, so I went over 3. And I just put those green arrows in just to, so you could see what was going on. They're really not part of the scatter plot. It's just more like cheating, to show you because we're just practicing, right? And then that person so had an X of 3 and then a Y of 5, and you see where the dot goes, right? And then here you can see where the fourth dot, or I'm sorry, the third dot goes because there's a 4 and a 4. And then here we have the fourth dot. So this is the scattergram of these 4 patients. Of course, a lot of times you have like hundreds of patients in there. But I just showed you the simple example. Okay, now because we did that, I can talk about linear correlation and you'll kind of get it, right? Linear correlation, that term, means that when you make a scatter plot of XY pairs, it kind of looks like a line. Now over here on the right is not like biology. That's not like statistics. That's like algebra, right? Because back in algebra, you'd have these perfect lines where the dot was right on the line and see the X and Y. Notice there's no diagnosis, nothing. That's algebra, right? So perfect linear correlation looks like graphing points in algebra. And if you actually make a scatter plot of like people XY pairs and you see that, you should suspect there's something wrong. It actually happened to me once. One of our statisticians came to me and said, Monica, look at this. You won't believe this. And I said, whoa, I don't believe this. What are you graphing? And he said on the x-axis he had put the weight of the person's liver, and on the y-axis he put the weight of the whole person. And I'm like, how do you weigh people's livers? Like, that sounds painful. And he goes, oh, let me go see. And what he learned was that you don't weigh people's livers. You use an equation to estimate the weight of their liver. And guess what's in the equation is their actual weight. So I'm like, that's why it came out like on a line, is because you were using the y to calculate the x. And he was like, oh, you're so smart for a secretary. So then I became an epidemiologist. But anyway, if you ever see this in biology, just suspect something's fishy because really things just don't end up right on the line. But if they get really close, you can say it's close to perfect linear correlation. I just wanted to let you know that's what's going on here with this linear correlation. Okay, so let's talk about facts about linear correlation. So things can be linearly correlated without being perfectly on the line. Obviously, our little thing was. So if when you make those dots, your scattergram, if you imagine a line going through it, if you imagine that the line is going up, like it kind of looks like it's going up, this is called a positive correlation. But you don't always have a line going up. So I want you to look at this, and I made up these data too. But on the x-axis is the number of patient complaints. So as we go on, the patients are madder and madder. They're grouchier and grouchier, making more complaints. On the y-axis, we have number of nurses staffed on the shift, right? And so as you go up, there's more nurses. Well, sure enough, when you got a lot of nurses, you don't have as many patient complaints, right? Because they're being attended to. So this is what you would say is, some people say inverse correlation, but in this presentation, I'm calling it a negative correlation because as one goes up, the other goes down, and as one goes down, the other goes up, because and that's depicted visually with this line going down. So you see, you can imagine a line going down. That's a negative correlation. Neither is better, positive versus negative. It just explains how these things are behaving together, how X and Y behave together. But then you can have situations where there's really no correlation, like X and Y really don't have anything to do with each other. So as you've seen, when you have patients in the hospital, some of them have really big families and those families come a lot, and some of them don't really have that many loved ones. So as you can see along X, here are total unique visitors, meaning you just count each person once. So you could have there's a patient who only has one unique visitor, but if you look at why days spent in the hospital, that person's been there 7 days and that visitor keeps coming, right? And then you have maybe a patient here, the second one, that is two unique visitors, and that person's only been in 1 day, but both those people have been there. Then you have people like a person with three unique visitors, and they've been in the hospital 4 days, right? And those are probably the same three people coming back. So it really doesn't matter how long a person's in the hospital. If they've got a lot of loved ones who keep coming, they'll keep coming or not, right? According to this correlation. So you end up imagining a straight line, and that's no correlation. That's fine too. Nothing is better or worse. It's just that you make the scattergram to try and understand how X and Y are related. This is always fun. Like in books, they always make some sort of goofy picture. I don't know why they do this. I would never get a goofy picture like they show in books about, this. I made up the correlation. This is in the lobby. The number of the games in the lobby and the number of the books in the lobby, they should really have nothing to do with each other. But if you see something just way goofy like this, just say it's no correlation. I don't even know how I'd get this. Hi there. All right. So we've been talking about correlation, and it actually has two attributes. So far, we've only talked about one, and that is direction. We talked about positive, negative, and no correlation. So whenever you're talking about a correlation, you have to say what direction it is. But you also have to say the other thing, which is what strength it is. So now we're going to talk about how you figure out what the strength is. So strength refers to how close to the line all of the dots fall. If they fall really close to the line, it is considered strong. If they fall kind of close to the line, it's called moderate. And if they aren't very close to the line, it is weak. Now remember, that's totally different from what direction it is. It could be positive strong or negative strong, right? It could be positive moderate or negative moderate. So this is just a statement. The strength is a statement of how close the dots you make in your scattergram fall close to the line that you end up drawing. So I thought I'd just give you a few examples. So look at this. I just made this up. This is what a strong negative one would look like. Notice how those pink dots are almost on the line. And this is a strong positive. Again, even one of the dots is on the line, right? Not all of them, or it'd be perfect, but it's never perfect. So this is really close, but it's strong positive. So strong just refers to the fact that the dots are almost on the line. Now this is almost the same correlation, but the dots are not really almost on the line. The line has to be fair and kind of go in between them, but they're kind of far away, and so just eyeballing it, you would say this is moderate. And here it gets weak, and mainly it's because the dots are more all over the place. But you'll notice there's one that's like right on the x-axis. And then, hey, look up there, like in the title, there's one up there, like way up there. And that's like an outlier. And sometimes when you get outliers, they can really whack things out. So even though this is a weak correlation, that line looks like so powerful because it's almost basically connecting these two outliers. So you just got to be careful, and that's part of why you make a scattergram first, is outliers can have a really powerful effect on a correlation, especially if it's in any of the four corners of the plot. Like if you get a weird outlier kind of in the middle, it's not going to do as much as if it's in the upper right, upper left, lower right, or lower left. It can really affect the direction, it's like a seesaw or a teeter-totter. An outlier can get on and really change the direction of it, and it can also mess with how strong or weak the correlation is. So that's why you really want to start with the scatter plot, and that's why the way this a chapter is organized starts with the scatter plot. Is you just want to look for outliers and also just see how x and y look when you plot them. Now we're going to get on to correlation, coefficient R. We're going to get on to computation and actually making a number so you can not just use watery terms like direction, positive, negative, or moderate, strong, weak to explain it, but you can actually put a number on how correlated X and Y are. So remember the word coefficient. We did it with coefficient of variation, which is different. So the CV, is one kind of coefficient, but what we're going to talk about is a different kind this time. Our coefficient this time is called R. And just coefficient means a number. We just like to use it in statistics. Now, it seems kind of weird because, like, I'm talking about correlation, and people are like, well, why is it R? Why isn't it like C for correlation? And I'm like, I don't know. I didn't invent it, but this is how you can remember it. You can go correlation, correlation. So, correlation coefficient R. So, just remember R means correlation. And technically, R means sample correlation. Population correlation coefficient, right? Like, because imagine you're correlating like height and weight in the population, like everybody in a particular state. You actually need a Greek letter for that, and I showed it on the screen. I don't know, it's this fancy P. I don't know the right name of it, but we don't actually cover it in this class, so I just wanted to show it to you. We're only going to focus on R, which is the sample correlation coefficient. So what is R? Well, it's like I said, it's the numerical quantification of how correlated a set of XY pairs are. And it's actually calculated by plugging all of the XY pairs into the equation. I'll show you how to do it. And you can see that if you do it by hand, if you have a lot of XY pairs, it'll take forever. So I try to limit that. And like, remember standard deviation and variance? There was like a defining formula and a computational formula. This time I'm only going to show you the computational formula. It's, in my opinion, way easier to do, but it gets you the same number. All right, so that's what we're going to do is we're going to take a set of XY pairs and we're going to calculate R. But then how do you interpret R? Well, let me just prepare you mentally for what we're going to get out of this calculation. The R calculation produces a number, and the lowest number possible is negative 1.0. So that's perfect negative correlation. So if we were like in algebra and we had a line going down and all the dots were on it, then the R would be negative 1.0, but that never happens, right? So if you want to think about it as like if you have a negative correlation and you get an R that's like negative 0.95 or something really close to negative 1.0, that it's close to negative 1.0. So it's close to perfect negative correlation. That's how you want to think about it. And then the opposite is the highest possible number you can get for R is 1.0, but most people never do that except for that one mistake I was telling you about. And that would be perfect positive correlation. So if you see that you calculated an R and it gets really close, like 0.95, like I said, or 98 or whatever, then you're thinking, whoa, this is really close to perfect positive correlation, right? And then everything else is in between. So like, 0.5 or negative 0.3 or 0.02 or negative 0.09, like all of those are between negative 1.0 and 1.0, and that's where R should be. So let's say you calculate R and you get 8. Okay, you did it wrong, right? Or you calculate R and you get negative 2.3. Like, that's not right. It's got to be between negative 1.0 and 1.0. And if you make a scattergram, you should know whether it should be on the negative side or the positive side, or it should give you a hint. So this is just more to calibrate what to expect from R, because it's kind of a big calculation. So I'm just going to give you some pictorial examples, because remember, every single time we make R, right, we also have a scatter plot behind it. And I just thought, it would be helpful to see some real life examples of R. These are real life examples, okay? Real life. You don't get this from just anything, right? I'm just teasing. But anyway, so I started with some negative R's because I'm feeling negative today. I went into the literature and I found this article about, oh, it's on MIT and Harvard. Ooh. Um, it's about the evolutionary principles of modular gene regulation in yeasts. And all I know is I'm supposed to cut down on eating bread. So that's all I know about this. But they had these really nice scatter plots. And they calculated R for them. And they had a little line on them. So I thought I'd show them to you. So if you look at the one that's labeled D, see where the dots are, right? And see where the line is. And this looks kind of like a moderate to strong negative correlation, right? Because the dots are kind of close to the line. And then when the group calculated R, they got negative 0.7. And so that kind of makes sense and then I put my opinion in the lower right. These aren't official cut points or anything, but I usually use these as a guide. See how I said negative 0.4 to negative 0.7 is moderate? So I would call that D1 moderate. Now let's look at E. So see how the dots don't cluster so close to the line as they do with the D1? That's going to make it a weaker correlation. It's still negative, right? So it's negative 0.44, and when you look at my little opinion, I still call that moderate, but it's on the low end. See that? And then if you look at F, see how many of them are like way far away from that line, and they're dragging it down. So now it's in the even a weaker correlation, negative 0.25, right? And so then that's weak. And so this is just some examples to give you a pictorial. And now I promise to be more positive. Here's some positive R's. They didn't draw a line on this one. This is a different article, right? It says obesity is associated with macrophage accumulation in adipose tissue. So again, try to cut down on bread. But anyway, if you look on the left side, you'll see all of these XY pairs plotted on the scattergram. And even though we don't have a line there, we can imagine it's going up, so we would expect this to be positive. But we also would imagine they're not really clustering around the line very tightly. So when we see that the R is 0.6, we're not surprised. I mean, it's on the high side of moderate in my world, which makes sense. But go look on the right one, under the B one, look at how you could almost connect the dots and get a line out of that. So that's really tightly hugging the line. And then we're not surprised to see that the R is 0.92. So that's pretty strong. So I just wanted to give you these pictorials before we actually went forth and calculated R, because that's one thing you can do is do the scatter plot, have an expectation what R should look like, and then if you calculate R and it's totally wacky, you know that you did something wrong. Okay, let's calculate R and let's use the computational formula. Okay, I threw the formula up in the upper left, and don't feel overwhelmed by it. We're going to take that apart very carefully, right? But before we even do that, I just want you to have a flashback to chapter 3.2. See all those sums of, or those capital sigmas in the equation? So we're going to handle calculating R a lot like we handled calculating variance and standard deviation. We're going to make like a table with columns, and then we're going to fill in those columns with calculations, and then we're going to add up the columns to get all those numbers. So already you were good at that in 3.2, you'll be good at this too. And then I made up a story because it's a lot easier to check your work if there's some story behind it in statistics. So pretend we have 7 patients that have been going to your clinic for a year. They're good patients, they keep coming. So they came to the clinic over the year, and at the last visit of the year, you measured their diastolic blood pressure. And what you predicted was, or what you thought would make sense, is those with a higher diastolic blood pressure would have had more appointments over the year because probably they're trying to stabilize their blood pressure, or maybe they have other problems that are driving it up. This makes perfect sense, right? So what you wanted to do is see if you were right. So you're going to take the diastolic blood pressure at the last appointment as your X, because you think that that's maybe the explanatory variable, or that would be the independent variable that would make it so have something to do with whether or not they had a lot of appointments. And then you take Y as the number of appointments over the last year, because you'd say, okay, if high DBP probably means they have more appointments. That's just your idea. Maybe you're wrong, but we're going to do that, okay? So I put in the title just a reminder, X is DBP and Y is number of appointments, so you don't forget. And then we made up this table. So look in the first column, it's just the patient number. It's nothing, exciting. We just want to keep track of which patient is what, right? And then notice under X, we just have all of their DBPs. So this um, patient 1 at the last appointment had a 70 mmHg, and patient 2 had 115 mmHg. That's kind of alarming. But these are fake data, so don't get worried about these patients. But anyway, we just fill in X, and then also when you have their chart out, you can look up how many appointments they had over the last year. And patient 1 only had 3, whereas patient 2 had like 45, which you can believe because sometimes they're coming in all the time to get stuff adjusted. Um, but then, patient 3 only had 21 and patient 4 had 7. So you can see these are the XY pairs for each of these patients, right? And it's pretty simple to go to the bottom and sum up each of the columns. We have sum of X's 678 and sum of Y's 166. And also, I'm reminding you of the R calculation. I put that in the upper right just so we can see what we're doing. I just want to call your attention to one of the terms in there, which is sum of X, which I put in the parentheses here. And that we already know now, just from making the first part of this table and adding it up. So we already have that thing in there. Now I just wanted to point out, if you saw the sum of X over here, it's not exactly the sum of X. It's a sum of XY. So the Y is mushed right next to it. That's not sum of X, that's sum of XY. And that's later in the game. We're going to put the sum of xy at the bottom of the last column. So that first term there, that's not sum of x, that's sum of xy. Okay, now downstairs we see the sum of x to the second, right? And that looks an awful lot like the one next to it on the left, which says sum of x to the second, right? And so how do you tell the difference between the kind without the parentheses and the kind with the parentheses? So this is how I do it. The rule is always, regardless of what's going on, do what's in the parentheses first. So that's easy to do if you have parentheses. If you got the parentheses version, you know that the sum of x to the second with the parentheses in it is you just do the sum of x and you do the sum of x and you times them by each other, right? But what if you don't have any? Well, what I do is I say, well, if I did have some, I do it this way. But if I don't have any, then I know I have to do the sum of the x squared column, right? So that's where you take x times x, x times x, x times x on each line, put it there and sum that up. So that's how I go through it, no matter where I am in statistics or algebra. If I see that sum symbol and then the x squared, I first look for the parentheses. If they're there, I know what to do. If they're not there, then I know you don't do the thing where you just take the sum of x squared. You have to go and look at the bottom of the column of the x to the second column and take the sum of that. I hope this is helpful. All right, so as you can see, there's I've shown you on the top of the equation is where you just take the sum of x and the sum of y. And on the bottom, I'm showing you where you take those and you take the square of them. And then in the other term is the one where you just take the sum of the column. All right? And so there you go. So what happened here? Well, we filled in x to the second. So if you go to patient 1, 70 times 70 is 4,900. That's where we're getting that number. So you go through, and then patient 2, 115 times 115 is 13,225. So you go fill all those in and you sum those up, and that's what goes in that first term over there. And then I'll bet you can guess what the next slide is. Surprise! Now we do the y one. So don't get confused because you kind of have to skip a column there. So 3 times 3 is 9, and so that's y and then y squared. 45 times 45 is 2025. That's how we're doing those. You sum all that up and then go look up at the equation. That's where you put that sum of y squared. Now we have xy, and this reminds me of a student I had before. She was really confused. She's like, Monica, I don't know what to do with xy, the xy column. And I go, what do you mean? I mean, it's pretty obvious. You just take x times y. Like here, 70 times 3 is 210. She goes, x times y? Where's the times? Like, how do you know it's supposed to be times? Like, I don't see any times. And I was like, you're right. I don't see any times either. Like, there's no, like how do you know to do that? Well, anyway, I'll just tell you, I guess. Imagine like a little multiplication symbol between x and y. That's what's supposed to be there. That's what you're supposed to imagine. I guess I was so used to looking at it, I was like, you're right. I don't know. I guess you're just supposed to assume that. So take x times y. So for patient 2, we just took 115 times 45, and that's how we got 5,175. So you go through each of those. This is a lot of processing. And then you sum it up at the bottom. Ooh, that's a big number. And then you see I circled it in the R equation. So I think we figured out where to put everything. Obviously n is 7, right? Because we have 7 patients. You see a bunch of n's in there. So I think we have all our R ingredients. So let's move forward. So all I did here was rewrite the exact same equation with all the ingredients in it, right? So like I said, the n is 7, and so wherever you see n, you'll see a 7. See that sum of xy on the top? You see where that goes. See sum of x and sum of y, and then downstairs you'll see I filled in all those numbers too. Now let me just talk to you a little bit about both levels, the numerator and the denominator. In the numerator, because we have order of operation, you need to do out the n times the sum of xy, that's 7 times 18,458. You need to do that out first, and then you need to do the other one, the 678 times 166 first. And then after you're done with those two things, you have to subtract the second one from the first one. That's the order you have to do that in to get the numerator right. Now for the denominator, it's a little bit the same, but a little more complicated. You see on the left side, you have that 7 times 67,892. You have to do that out. And then you have 678 squared. You have to do that out. Then you have to take that, subtract it from the first one, and after that, after you have that, you take a square root of all of that, and that's your first term. And then you still have to go over to the other one. You have to take 7 times 6,768, keep that. Then take 166 times 166, keep that. Then that term you subtract from the first one, and after you're done with all that, you take the square root of that, and then those two things you have to multiply together. So that's a lot of work, and you have to do it in the right order. So here, I just wanted you to see how you probably want to just work out this term separately first, and then work out this term separately. And just like that thing I was telling you about xy, those two terms, once you work them out, you take the square root of the left one and the square root of the right one, you have to multiply them together to get the denominator. So this slide is to help you see. I threw the numerator on, that was relatively easy. But these are the two different numbers you should get from the left side of the denominator and the right side of the denominator, just to check your work. And then, of course, once you multiply them by each other, you get this number, 17,561.3. So ultimately, what the calculation for R comes down to is you're trying to calculate the numerator and you're trying to calculate the denominator. And at the end, you divide the numerator by the denominator and you get the answer, which is R. So we're going to do that now. And here's what we got. We got 0.949. And because we see that it's positive, then we know it's a positive correlation. And then remember my opinion, and also probably everyone's opinion, because if you run that up, you go 0.95. Well, that's getting really close to 1.0. So most people would agree that that's pretty strong. So how you would diagnose this correlation is you would say it's positive and it's strong. Okay, I just want to wrap this up by giving you a few facts about R that I may not have covered yet. First, R requires data with a bivariate normal distribution, which is something we didn't check before doing our R in this class because I just don't cover that. But please know, if you take another statistics class and they bring up R, they might talk about checking for the bivariate normal distribution. So just know about that. Next, please know that R also does not have any units. So other things that don't have units, remember the coefficient of variation didn't have any units? Some things just don't have units, and R is one of them. Also, we did talk about how perfect linear correlation is where R equals negative 1.0, that's if it's a negative correlation, or R equals 1.0, which is a positive correlation. But I might not have mentioned that no linear correlation is R equals 0. Now you probably won't see that in real life, but sometimes I'll make an R and the R is either positive or negative, but it's 0.000000000 something, right? Regardless of whether it's positive or negative, if it's 0.00000 something, it's really close to 0. So that means there's probably like no linear correlation. And then we learned about positive R and negative R, but I just wanted to remind you of the behavior of X and Y when you get those circumstances, okay? So if you have a positive R, it means as X goes up, Y goes up. But it also means as X goes down, Y goes down. So they travel together. When you get a negative R, it means as X goes up, Y goes down. But also it means opposite. As X goes down, Y goes up. So they travel in the opposite directions. Now here's another fact about R, a little factoid. If you choose to switch the axes, like let's say I designate, you give me XY pairs and I designate a certain variable as X and a certain one as Y, and you actually designate them the opposite, it really doesn't matter even in the equation because you'll end up with the same R value. So it doesn't matter if you call the X my X Y and I call your Y X, like we can switch them, but you'll still end up with the same R with the calculation. Then finally, even if you converted X and Y to different units, you get the same R. So let's say that you were in England and you were doing the correlation between height and weight and you were using the metric system on the same patients that I was using the US system. Even though we'd have different numbers, because obviously you have to convert them, we'd still get the same R when we were done. So finally we get to the last subject of this lecture, which is lurking variables, which you've heard about before. But the main point I want to make is correlation is not causation, so you don't want to be misled by correlations. So beware of lurking variables. So remember, lurking variables are things lurking behind the scenes that cause things, right? And so you may have realized that selecting X and Y, like if you have XY pairs, designating which one is X and which one is Y is kind of political because you're implying that X could cause Y. So let's say that you're correlating height and weight. Taller people are heavier, so you would cause X to be height and Y to be weight. People don't go, oh, I'm too short, I should gain weight so I can grow taller. That's just not the way things work. So you have to put X as the height and Y as the weight. But there are, in reality, other causes of weight besides height. In fact, there are things that cause both height and weight, like genetics, right? So, a genetic profile that leads to tallness and also obesity could be a lurking variable in the relationship between height and weight. So, there could be some tall people that are always obese, and it's not really just because they're tall, it could be because they have the genetics that program them to be tall and also obese, right? And so, here's an example where you got to be real careful with correlation. So there's been this claim that eating ice cream causes murders because they notice when in areas where ice cream sales go up, murder rates rise. And I don't know about you, but when I have some really good ice cream, it just makes me so mad. I'm just kidding. I mean, why would this happen, right? Well, the reality is summer and warm weather are lurking variables because we sell more ice cream in the summer. The ice cream consumption goes up, but also people are outside more and more murders occur. And I'm from Minnesota where it gets really cold for periods of the winter. And oh my gosh, there are totally no murders then. Like people just don't commit murders when it's really frigid out. It's just really inconvenient. So that's a situation where there's a lurking variable. And so you don't want to start, screwing up our ice cream laws and making it so we can't have ice cream just because you misappropriate that ice cream causes murders, right? There's a lurking variable behind it that's having something to do with both. Here's another one, and this was my professor in my biostatistics class used this. He put up a really like a time series chart over a long time, like since the 1900s. And he pointed out as people purchase more onions over time, as onion consumption goes up and down, the stock market rises, right? So when the stock market's low, people aren't eating as many onions. And this is just true over generations in the US. So, yeah, we've had some problems with our economy in the US. Do you think we should all start eating a bunch of onions? Right. So the healthy economy is a lurking variable. In a healthy economy, people buy more food, including onions. And also, a healthy economy boosts the stock market. So you got to be careful about this. Correlation is not causation. And so if you want to make the stock market go up, don't make everybody eat onions, and definitely don't make us stop eating ice cream. That would make me very upset. So at the end of the day, you're not going to be able to affect the murder rate by bringing down the ice cream consumption rate. And you're not going to be able to fix the stock market by making people eat onions. And so that's the whole concept behind lurking variables, and correlation is not necessarily causation. So in conclusion, when you're doing your correlations, first make a scattergram because you want to get an idea, a visual idea of the strength and the direction, and you also want to look for outliers. Then go on and calculate R by hand, but be really careful because it's a big hairy calculation and you don't want to make any mistakes. And then finally, when you go to interpret R, be careful of lurking variables and remember that correlation is not necessarily causation. And now, time for some ice cream. Hello, it's Monika Wahi, your library college lecturer, here to ruin your day with Chapter 4.2, Linear Regression and the Coefficient of Determination. So at the end of this probably painstaking lecture, the student should be able to at least explain what the least squares line is, identify and describe the components of the least squares line equation, explain how to calculate the residuals, and calculate and interpret the coefficient of determination, or CD for short. All right, so it's really cool if you have a crystal ball because then you can make predictions, right? You just look into the crystal ball. It's some nice equipment. I've had friends who have them. They're very nice to put out on your dining room table as a centerpiece. Unfortunately, though, they don't really play much into statistical predictions. So what I'm going to show you in this lecture is how we use statistics for prediction instead of this beautiful crystal ball. So we're going to start by talking about what the least squares line is, and then we're going to talk about the least squares line equation, which is the crystal ball thing we use only in statistics, okay? And then we're going to talk about dealing with prediction using the least squares line. And finally, we're going to talk about the coefficient of determination. So let's get started. And let's get started with the term least squares criterion, right? So remember, criteria is plural and criterion is singular, and it means, well, criteria as stuff you need to meet, right, to be eligible. Like you have to meet the criteria for registration for college, right? Well, least squares criterion is just one, which is awesome because then you only have to meet one thing. So one of the things you probably wondered when you were watching the last lecture is, how do you know exactly where to draw this line when you have a scatter plot? Like, how do you know where to make the line the most fair? So in the last chapter, when we plotted the scattergrams, I just drew a line there for demonstration, but there actually is an official rule as to where the line goes. Okay, and basically the rule is it has to meet the least squares criterion. Okay, if it meets that criterion, there's only one line that does, then that is where the line goes. So how do we get to that? Well, this is roughly what it looks like. When you draw the line, there is a vertical distance from each of the dots to the line. Now, as you can see by the slide, sometimes the dots are below the line and sometimes they're above the line. And so the word squares indicates that whether it's up or down, you're going to square it so it's not going to be negative anymore, because whenever you square a negative, it becomes positive. So first you're going to have to square all of these things. Okay? So imagine you were just going to try it out. Like you maybe draw this line and then you calculate the squares and you'd be like, okay, that's how many. And then maybe you tilt the line a little and calculate the squares again. And your goal would be to add, when you added up all the squares, to have the least ones. So the line belongs where it would cause the smallest sum of squares for the whole data set. So if you're software, which you're not, you're a person, right? But if you were software, you'd be figuring that out using your software brain, of how exactly to tilt this line and where exactly to put it to minimize these squares. But we're people, so I'm going to go on and explain how people do this. So the trick is, if you can figure out where the line goes, you can draw it on the scatter plot and be right. But there is a challenge of knowing exactly where it belongs on the graph. And then also, you're probably realizing you don't always have a graph to draw it on. Like maybe you need to talk to somebody about where the line goes and you can't draw them a picture. So, how you explain where the line goes is you use an equation. And some of you may remember this and some of you may not. So, I thought I'd do a little quick review about how lines and equations relate. Okay, so we're going to get into the least squares line equation. But first, I'm going to give you a little flashback about algebra, and I'm sorry if this is painful. This is hard for me because I wasn't really that good at algebra. But and this isn't statistics, this is algebra, but I just wanted you to remember this part, okay? So back in algebra, there was a chapter where you were given these XY pairs, and it was different from statistics because they all lined up on a line. See, these pink dots are just perfectly on a line, okay? And these are the XY pairs. And remember, you had to graph this, kind of like we had to do scatter plots. And then you were given this equation, y equals bx plus a, right? And that was the linear equation to describe this line. And you were like, okay, I don't get how to put this equation together with this line. And so first the teacher would say, well, B stands for the slope of the line, right? Because you have to know the slope. I mean, the line can be tilted any which way. And so if you know the slope, you already know something about the line. And in algebra, how you would make the slope is you calculate the rise over the run, right? And so there, B in algebra was rise over run, and you'd get the slope. And then you'd be like, great. But you always needed another thing in order to define the line. Because if you imagine this line is in an elevator, it could still have the same slope, but go up or down, right? So we need to anchor it on the y axis somewhere. So A stands for the y-interceptor, where it spears through the y-axis. And as you can see by the drawing, it looks like A is 0, comma 0, right? But you don't have to look at it. What you can do in algebra is, to get A, is what you would do is go, since you'd filled in B, you just go grab an XY pair and plug the X in and plug the Y in and plug the B you just got in and back calculate the Y intercept, right? And that's how you would get the whole linear equation. And so that's how you would do it in algebra. And I just wanted to remind you of that because we do some similar things in statistics. It's a little different, but I wanted to remind you how to connect what a line looks like with how this equation works. All right? Well, welcome to statistics. Look, those pink things are not on a line. So we want to make a line, but now you know about the least squares criterion. What you're trying to do is make a line that minimizes the least squares, right? So here we go. Remember how I was just talking about this linear equation back in algebra? Well, notice the difference. The main difference here is the hat, right? The Y is wearing a hat. And that's universally in statistics. Whenever you see a letter or a number wearing a hat, it means it's an estimate, okay? So of course we're estimating Y, because if you look on that line, none of these dots actually falls on that line. And we don't really expect even an estimate to fall on that line, just close, right? Because of the least squares, okay? And so we almost have, in a way, the same goal we did back in algebra. We have to get that B, that slope. And then we have to use that to back calculate our A. Okay, so let's go on with that. So like I said, in the software approach, you just feed all the XY pairs in, and then the software just actually prints out the B and the A. It just prints out the slope in the y-intercept, which is why I love the software. But we don't get to use that in our class. In our class, we have to do the manual approach just because it's painful, and I had to do it too, so now I'm making you do it, right? Mean. Okay, what we'll do is plug all the XY pairs into an equation to get this slope, this B. And I promise you, I won't give you a ton of XY pairs, or you'll be there forever. But this next step we have to do, we didn't have to do in algebra, and that is we're going to have to go back to all of our x's, calculate x bar, and go back to all of our y's and calculate y bar. Remember, that's the mean of the x's and the mean of the y's. And you're probably wondering, well, why do we have to do that? I'll show you again, but in case you didn't notice, those dots really didn't fall on the least squares line. They fell around it. And you need a dot at least on that line to help back calculate that y-intercept. And the rule of the least squares line, one of the rules of it, is that x bar comma y bar is on that least squares line. So you can know if you calculate that out that that's actually on the least squares line. Okay? And so finally, after you do x bar and y bar, you plug in B, and you plug in x bar for the x, and you plug in y bar for the y hat to back calculate the A. So it's a similar but different process as algebra. So the moral of the story is you need to recycle, right? We got to be good to the environment. So what has happened? Well, you wouldn't be at this point in your life of making a least squares line if you hadn't already started out by making a scatter plot and then deciding you wanted to do R and then making R. And when you make R, you end up with that big table, remember, and you end up with all these calculations like sum of x, sum of y, sum of x squared, and sum of xy. Now you want to recycle those. You want to save those calculations from R because they fit also into the equation for B. So you want to recycle that. Also, you want to save the R you made because you're going to recycle that into the coefficient of determination, which I'll explain later. And then this is not about recycling. You'll actually have to make this anew, but you need to calculate x bar and y bar now. You never needed to do that before now, but now you need this. And so get together your old R calculations and then put your x bar and y bar together, and you'll be ready to do the least squares line equation. All right, so here's a flashback. Remember this big table? Remember our story. We had 7 patients, right? And X was their diastolic blood pressure at the last visit they had of the year. And then Y was the number of the appointments they had over the year. And we thought, well, if your diastolic blood pressure, goes up, then maybe you need more appointments because it's a marker of being sick. I don't know. That was my little story. Okay, so over on the right now, we'll see that the formula, we have the formula we're using for B. The text gives you 2 formulas. Again, I've always got my favorite. It's the one with the table, right? So here's the formula for B. And then after you calculate B, you'll notice in the formula for A B is in the formula for A. So you got to do B first, right? So a lot of times students are a little confused on what the goal is here. The goal is to, if you look at the bottom of the slide, the goal is to come up with what B is and what A is, and then fill it in, and that's your least squares line equation. So your least squares line equation is always going to have a y hat in it. That's a variable. That just gets to stay there. It's always going to have that equals. And then after that, whatever your B is going to be mushed up next to that X. So it's always going to have that X there. And then plus, and then whatever you get for A. And just as a trick, if A turns out to be negative, then it ends up being minus A, right? But that's the generic equation, and our goal is to calculate B and A and fill them in, and then we will say this is our least squares line equation. Remember how I was saying you actually need to make some new calculations, right? So you need to make y bar and you need to make x bar, and it's a little easier to show when I've got the columns up. If you look at the bottom of the slide, remember how sum of x was 678, and remember how our n is 7, and remember how sum of x divided by n is your x bar, and the same goes for y, right? We have the sum of y divided by 7. I just wanted to quickly remind you of this, that you need to generate these things before you can actually completely finish the least squares line equation. I just summarized, I cut to the chase basically. I just summarized the actual numbers you're going to need and put them over here, so we don't have to look at that whole big table anymore. All right, and you'll notice that I grayed out the sum of y squared because I realized later we don't really use that. Okay, so let's look under on the left side under the big list of numbers we have. And you'll see the B equation that I filled in, right? And if you compare that to the formula on the right side, you'll see what's going on. You know, that n is 7, right? So wherever you see that 7, that's where n is, okay? Then the top of equation, remember sum of xy, let's just look that up. Yeah, that's that big number, 18,458. I wanted to just be clear. You have to do out that left side, the 7 times the 18,458. You have to do that one out. And then do out the right side, which is that sum of x times sum of y, which is 678 times 166. You have to do that one out. And then after that, you have to subtract the right one from the left one because of order of operation. Okay, so that's how you make the numerator. Now let's just look downstairs. Again, we have an n, so we know that's 7. And then that's sum of x squared. And remember, it doesn't have the parentheses around the sum of x squared. If it had the parentheses around it, you'd be taking like 678 and squaring that. But it doesn't have the parentheses, so you have to use that big number, 67,892. Okay? And again, like with the upstairs, you got to do out that side of the equation, right? That term, you've got to multiply that out before even looking at the rest of the equation, right? And then, oh, here we go. On the right side of the denominator, we have sum of x squared. That's exactly the example I was giving earlier. So you say 678 times 678, and you have to do that one out, right? And then after you do that one out and you do the first one out, then you subtract the second one from the first one. Remember, order of operation. And if you do it right, you should get, see below the on the left side of the slide, you should get that for the numerator and that for the denominator. And then you divide them out and you get 1.1, and that's your B, right? So there you go. That's how you do it. And so now we've got to worry about A. So what I did was I just wrote B at the top there. So B is 1.1. And so now we can use B to try and figure out A. So remember how, look at my list. Remember how I did X bar and Y bar for you, just so we had that ready? So now we're going to calculate A by putting in Y bar minus, and remember order of operation again. We got to do the B, which is 1.1, times X bar. So we do that one out first and then subtract it from 23.7. And remember how I was saying sometimes you get a negative A? Well, we got negative 80 for A. All right? So we got our B, we got our A, and let's go. Now, if you want to check your work, this should work out, right? Like you should be able to take the B times the X bar, right, which is 1.1 times 96.9 minus 80, you know, the A, and you should get 23.7. So if that works out, then you know you did everything right. But remember what the goal was? The goal was to actually fill in that least squares line equation. So if you look over on the right, that's what we did. So we still have our y hat, we still have our equals. Now we have a 1.1 where the b belongs. We still have that x because those are variables, that y hat and the x. And then we do minus 80 because we came out with a negative one. If it had been just plain 80, we would say plus 80, okay? All right, at the beginning of this presentation, I teased you that we were going to do prediction with the least squares line equation. We weren't going to use a crystal ball, we were going to use this equation. Well, I finally get to that exciting part of this presentation. But, and there's always a big but, I first have to warm you up with some rules, right? First of all, I just want you to reflect on what we just did and realize that we can draw out a least squares line, but unlike algebra, our xy pairs probably aren't on it, right? Like in this example, none of the xy pairs are on it. So you need to be sure about at least one xy pair that's actually going to land on the least squares line. And the only one that you can be sure of is going to land on the least squares line is x bar comma y bar. And if you reflect on it, that's why we had to calculate that, right? Because we had to use x bar and y bar in the calculation to back calculate A, the y-intercept. Now, you may be lucky and get a data set that there is an xy pair that just happens to fall on the least squares line, or maybe even a couple, or maybe more. But you can't trust that. So if you need to trust that there's a point on the least squares line, you know it's always going to be x bar comma y bar. All right. And now I want to focus more succinctly onto the slope, or b, right? So remember, we just in our example calculated b and we got 1.1 for b, and that's the slope. So I want to point it out that the slope b of the least squares lines tells us how many units the response variable, or y, is expected to change for each 1 unit of change in the explanatory variable, or x. So that's a little kind of a tongue twister, but if you think of our example, it's a little easier to understand. So the fact that that slope was 1.1 in our example, and that we were having xb dBp and yb number of appointments over the last year, what we're essentially saying by that is for each increase in 1 mmHg of dBp, or the x, for each increase in one of those, there is a 1.1 increase in the number of appointments the patient had over the past year. So as dBp goes up by 1, then the appointments goes up by 1.1. Well, I don't know what 1/10 of an appointment is, but you get what I'm saying, because it's just a y hat, okay? And so the number of units changed in the y for each unit change in x is called the marginal change in the y. So, which, if you sort of think about it, that's 1.1. So 1.1 is a slope, but 1.1 is also the marginal change in the y for each unit change in the x. Now I also want to just recall for you this concept of influential points, right? So like with R, if a point is an outlier, and remember we should have done a scatter plot and everything before we got to this point, because we need R, we need all those sums of x's and sums of y's and sums of sums and whatever, right? And so like with R, if a point is an outlier, and you can see it on the scatter plot, it can really drastically influence the least squares line equation, just like it can screw up R, right? And so an extremely high x or an extremely low x can do this, and I was just, pointing out a culprit we have here on the scatter plot. So always check your scattergram first for outliers, because you could end up in the situation where you're making a least squares line and there's a bunch of outliers, whacking it out. Okay, now I'm going to also bring up, you're probably like, when do we get to the prediction part? And I'm like, you just have to relax. I have to get through a few of these issues, right? So one of them is the residual. And the word residual, like it kind of sounds like residue, right? Like you said, somebody comes over and sets their cup on your coffee table without using a coaster, and it leaves some residue and you get all mad. Okay, well that's kind of what a residual is. It's like kind of like residue. It's like something left over, right? So once the equation is there, once you make the least squares line equation, there's something I just want you to notice. And that is, you can take each x. Remember how we had 7 patients? They each had an x. You can theoretically take each x, plug it into the equation, and get the y hat out, right? So I want to just demonstrate doing that. So we have our equation upper right here. So patient 1, I took patient one's x, which was 70, and I plugged it in, 70 times 1.1 minus 80, I put it in the equation, and I got -3. Now that's y hat. The real y, I put it on the screen here, is actually 3. So as you can see, it's not the same answer, right? And then patient 2, I did it with patient 2 also. I did 1.1 times 115 because that's the x, and then minus 80, because that's the rest of the equation, and I got 46.5. Now that was a little closer because look at patient 2's y's. That was 45. It's really close to this 46.5. That was a little bit better. But the reason I was doing all that is I just wanted to tell you the residual is y minus y hat. So in the first case, we have y hat was -3 and y was 3. So patient 1, we did 3 minus -3 and we got 6. So that's the residual. It's kind of like residue, right? It's like the residue left over between y hat and y, right? And then patient 2, we did it again. We took y, which was 45, minus y hat, which was bigger. It was 46.5, so we got -1.5. So that's the residual. So, so this is how you calculate the residual, and this is what it is. This is how you get it. But the bottom line is, you don't want big residuals, right? Because that would mean the line didn't fit very well. So you'll find that if you have a really good fitting line, you have very small residuals. And so you're probably like, well, what's a good fitting line? Well, we'll get to the coefficient of determination, and that'll help you see what constitutes a good fitting line. But first, I will get to the prediction part. Okay, so you're done with your least squares line equation, and you want to use it for prediction. So let's say you knew someone's DBP and you wanted to predict how many appointments she or he would have in the next year. Now what you're not doing is you're not reusing your x's from your data. We just did that to make the residuals. What you're doing is actually imagining a new thing out there, and you're going to use this equation for prediction. So you could plug in the DBP as an x and get the y hat out and say that's your prediction, right? But you gotta use some caution. If you use an x within the range of the original equation, as you can see, I put the x's up here. And the range of the original equation was like 70 to 125, right? Those were, the areas covered by x, right? If you do that, if you pick an x somewhere in there, this type of prediction is called interpolation, and people feel pretty good about it. But if you use an x from outside the range, like one that's really smaller, like 65, or one that's bigger, like 130, then it's called extrapolation. And then it's not such a good idea because you don't know if it's really going to work, right? So here I'm going to give you an example of interpolation. The patient in your study has a DBP of 80. Okay, so 80 is right in there. It's in that range. So let's use it, right? So we do it now. This looks familiar to you because we just did this when we did residuals, but we're using a new person now. So 1.1 times 80 minus 80 equals 8. So this is how what we would do is predict that this patient would come to 8 appointments next year. So that's how we use our least squares line equation like a crystal ball where we can predict, right? So is it really this easy, right? Is this all you have to do to predict the future? Well, it's not really that easy. You can't make a linear equation out of any old xy pair. So remember this from our last lecture. See this scatter plot? It looks like, what, a cloud of gnats, right? It doesn't have a linear equation. It doesn't look like you should make a line. But you know what? You feed that stuff into the software, or you feed that stuff into your B formula and your A formula, you'll get a line out of it, even if there's no linear correlation. And so if you get that line out of some scatter plot that looks like this, then it's not a very good line, right? And it wouldn't work very well for prediction, right? Because this looks pretty unpredictable. So for that reason, we can't just accept any line that is handed to us. To evaluate if our least squares line equation should be used for interpretation, we need the coefficient of determination. So here we are at the coefficient of determination. And so remember how I said you have to recycle, recycle, recycle in this? Well, get out your R, time to recycle R. So the coefficient of determination is also called r squared, and it literally means r times r. And I just have to add this on. Just like, remember the coefficient of variation? Remember that one? We always turn r squared into a percent, right? And so you times it by 100 and put percent. So in this example that we did, remember early on in the last lecture, we did the r for this, that not the scatter plot I just showed you, but for the one of DBP and the appointments, right? And we got an R that was really, really strong positive correlation, right? We got 0.95. Well, if we want to calculate R squared, which is the coefficient of determination, we take 0.95 times 0.95 and we get 0.90. But we got to do that percent thing, so we end up with 90%. So this is how you say it. You say that 90% is the variation that's explained in Y by the linear equation, right? So that's, Y varies, right? Like how many appointments they had, was different for each person. Well, 90% of that variation is explained by the equation. And of course, if you take 100 minus 90%, there's 10% unexplained variation. So there's still some variation that could be explained by other variables, but not a lot. And how you actually state it is, when you be done with this, if you were writing a paper, you'd say 90% of the variation in the number of appointments is explained by DBP. And I know people are like, explain, like it doesn't have a mouth. Like, what is it talking about? You just have to say it this way. It's statistics ease. This is how you say it. And by contrast or by complementary, what you would say is 10% of the variation in the number of appointments is not explained by DBP, right? It could be explained by other things. Well, we happen to get a nice, I say CD for coefficient of determination. We got a nice high one, but what if it's low? Well, let's just think about it. CD should be better than at least 50% because that would be random, right? And the higher the better. So if you're on a test, nobody's going to give you a CD of like 60% and say, is this any good? Because, I don't know, you'd be very conflicted. In real life, what I use it for is to compare models. If one is 60% and the other is 55%, of course I'm going to go with the 60% one, but it's still not very good, right? And if it's low, the higher the better, basically. And if it's low, it means that you probably need other variables to help the X you use to explain more of the variation, because that X is not doing it. Okay, in summary, I just wanted to go over chapter 4 so you realize where we've been. Okay, so we started out with a set of quantitative XY pairs. First thing we did was we made a scatter plot. We wanted to look at the linear relationship between X and Y, and we wanted to look at outliers. If we had seen a lot of outliers or no linear relationship, we would have stopped there. But because this is a class and we had to learn, I forced there to be a scatter plot with a linear variation and not too many outliers so we could move forward and do R. So we calculated R to see if our correlation was positive or negative and weak, moderate, or strong. So that's what you do if you find a linear relationship. Next, in addition, in this lecture, we calculated B and A to come up with the least squares line equation. And I just wanted you to notice that the sign on B will always match the sign on R. So if you have a positive R, you'll have a positive slope. If you have a negative R, you'll have a negative slope. But otherwise, the numbers won't match, just the sign. And then also, I wanted you to notice that strong correlations will give you high coefficients of determination, even if they're negative correlations, because remember it's R times R, and so negative R times negative R still is positive, right? So if you have strong correlation like negative 0.9 or 0.9, it really doesn't matter what direction. If it's strong, then you're going to get a high coefficient of determination. So after we did this B and A thing, we used that linear equation to calculate residuals, right? Like we took the x's from the original data and put them in, got the y hat, and calculated the residuals. After that, we used R to calculate the coefficient of determination, or CD, to decide if we wanted to use the linear equation for prediction, because if it was bad, we weren't going to do that. But we decided it was good for prediction at 90%, and we decided to use it. So that was our journey through these XY pairs all the way down to the coefficient of determination. Good job, you made it. So in conclusion, the least squares criterion and calculating the least squares line was the first thing we went over, how to do that and what it all means. And then I reviewed some issues with prediction using the least squares line because it looks kind of easy and looks kind of, um, better than sliced bread, but there are some things you have to think about. Finally, we went over the coefficient of determination so that you could figure out how good your least squares line equation was. And I just wanted to point out that CD kind of looks like CDs, like we used to have CDs. They were so pretty and rainbowy like that. But now all CD means is coefficient of determination.